Hi everybody, it's good to rejoin you today and continue on with section 8.3, quadratic functions and their graphs. We're going to be doing section 8.3 part 2 in this video, and at the conclusion of part 1 we came up with a formula for finding the x value of the vertex. And now in this second video, we're going to be looking at two different quadratic functions and graphing each one of them on a coordinate plane, and then responding to a few other questions that you need to as well be aware of as we move through the finality of this section. So today, I'm going to kind of direct your attention to the board, and there's quite a bit of information that is up here on the board, and I'm going to try my best to get through it and at the same time stay out of the way of the camera so all of the necessary things can be shown to you. The type of quadratic function that we're looking at in this video is the one that we actually spoke about in the first video. The value of function f when the domain is x is equal to ax squared plus bx plus c. This happens to be the standard form of a quadratic function, and it's typically the most common form of how a quadratic function will look like. And here are the directions as to what we're going to do with two different quadratic functions in this video. Some of these things that are on here we haven't talked about yet, but as we move through the graph and the work that we're going to do, we'll explain these other items that we're going to expect you to be aware of. So here are the directions for the two different quadratic functions that we're going to graph and then identify some things about. Graph each quadratic function using the vertex and two pairs of mirrored points. I'm going to stop right there. There is going to be a total of 5 points that you're going to be asked to come up with in order to graph the parabola. One of those points, the precious point of the mix, is the vertex. That's point number 1. And then we're going to come up with two pairs of mirrored points. One ordered pair that's going to represent mirrored points, and a second one. A total of 5 ordered pairs are going to be plotted on the coordinate plane for us to come up with the finished graph. And then once the graph is done, we're going to identify the following items. Letter A, we're going to identify the axis of symmetry. That from the first video was the imaginary vertical line, the dotted vertical line that passes through the vertex and cuts the parabola exactly in half. We're going to identify the axis of symmetry and give you the definition of what that, how that axis of symmetry is going to be identified. B, something that we've already actually done back in a prior chapter, we're going to define the domain and the range of the graph. We're going to do that. And letter C, we're going to identify, first of all, whether this graph that we're looking at has a minimum or a maximum value. It can only have one of them. It's either going to be a minimum value or a maximum value, and we're going to identify where does that minimum or maximum value, where does it occur. That will be very, very basic. I can tell you this before we move on. The things that will need to be identified, letter A, letter B, and letter C, all three of them are linked to the vertex. So the vertex is a very key point, to say the least. Folks, there's one other thing I just want to say before we move on. When you go to your textbook and you go to 8.3 and you look at the directions of how the author is going to graph these quadratic functions of how we're going to do ours today, you're going to see a completely different method shown in the book. I'm not discounting that method, but I think it is way too much work that needs to be done just to be able to take a quadratic function and come up with the necessary ordered pairs that we need to come up with and graph the finished product. I think they are asking for a lot of information. I understand where they're coming from, but I think they're asking for a lot of information that we just don't need to be concerned about doing. So please understand this as you're viewing this. I'm not doing it the way that the book will do it in 8.3. Now, here's the item number 1 that we're going to do. Here's number 1. Here's the quadratic function. F of x is equal to 3x squared plus 12x plus 8. That's the quadratic function that we're going to graph. I told you in the first video, the first thing that I'm just going to identify is I want to know, before we get into the work of this, I want to know how that parabola is going to open. And how it's going to open, like we mentioned, is hinged on the coefficient of the quadratic term. Your A. Your A. Your A. A is a positive 3. If A is positive, the parabola is going to open upward. So I just want to make sure that I note that to myself. If it's going to open upward, then the parabola is going to have, when its vertex gets plotted up here, it's going to be the lowest point on the graph. And it's also telling us that it's going to have a minimum value, not a maximum value. Lowest point on the graph corresponds to minimum value. Highest point on the graph for the vertex corresponds to maximum value. So this one is going to have a minimum value as we move through it. So we know it's going upward. And now the first thing that we need to do, we need to identify the vertex. And to get the vertex, the first item that we need to find is the x value of the vertex. Here's our ordered pair, and here's basically the instruction of what we're going to have to do to get the vertex. First item, we need to find the x value of the vertex. And that means we need to know the value of b and we need to know the value of a, because the x value of the vertex formula is the opposite of b over 2a. Your a is 3. Your b is 12. We don't need c to find the x value of the vertex. So I'm going to substitute those numbers into this formula, and we're going to get the x value of the vertex. And people, just so that you know what I'm going to do, when we get that x value of the vertex, I'm going to put that x value of the vertex as the x value of the middle point that we're going to come up with. This block right here is going to be filled in by the x value of the vertex, and the square right below it is going to be the value of f of x, or the value of y. It's going to be the y value of the vertex. The vertex point, that ordered pair, is going to be placed right in these middle two boxes, top and bottom from one another. That's where the vertex is going to go. So let's get the x value of the vertex. I'm going to bring down the opposite sign. The value of b is 12. That's going to be written over 2 times the value of a, 2 times 3. That's going to give a negative 12 over 6, and that's going to give us a negative 2. Negative 2 is the x value of the vertex, and we'll place that right here. Now we need to get the y value, and here's how we get the y value. We're going to evaluate this function for the domain of the x value of the vertex. We just found the x value of the vertex is negative 2. Now we're going to find the y value of the vertex, and we're going to evaluate this function when the domain is the x value of the vertex, negative 2. And now we're going to substitute negative 2 into that trinomial, and we'll have 3 times negative 2 squared plus 12 times negative 2, positive 8. I'm trying to keep some things clean as we do this. Let's come down with that equal sign, and let's follow the order of operations. We need to do this power first, so you bring down the 3, and that's going to get multiplied by the evaluation of negative 2 squared, which would give us a 4. I'm just going to bring down the rest of this stuff. And then we'll have 12. Negative 24. Positive 12 times negative 2, negative 24, positive 8. Now with a limited amount of space, we should have enough information here to find the value of f when the domain is negative 2. 12 coupled with a positive 8 is 20. And 20 combined with a negative 24 would give us a y value of negative 4. So we now have the vertex. The vertex of this quadratic function is negative 2, 4. Now I know it doesn't necessarily look like an ordered pair, but there is a reason why I made the display of the chart moving horizontally as opposed to vertically. Now I'm just going to kind of erase some things up here before we move on with this problem. I'm going to get rid of all of that work because we're going to need this space up here to find additional points that we need. Now there's the vertex. These two regions right here, the two boxes on opposite sides of the vertex, are going to give us the ordered pairs for the first pair of mirrored points. The first pair of mirrored points are going to go in these boxes right here. And here's all that is necessary for you to do. You come to your table and you look at the x value of your vertex, which is negative 2. A truth that I think we mentioned in the first video was this. If I didn't mention it, we'll mention it right now. Any pair of mirrored points, the x values of any pair of mirrored points will always be the same distance away from the x value of the vertex. Now let me repeat that. The x values of any pair of mirrored points will always be the same distance away from the x value of the vertex. Now here's one reason why I made this chart go horizontally. I'd like you to think of maybe this line going through the middle that's separating x from y as maybe being a number line. And just think of right here on this number line, this represents an x value of -2. If we go 1 unit to the right on that number line of -2, 1 unit to the right of -2, that's going to give us -1. So we're going to let this x value of this point be -1. What did I do? I actually moved 1 unit to the right from where I started at -2. I actually did this. I actually took -2 and I added 1 to it, and that gave me a -1. But in terms of a number line, the first integer to the right of -2 would be -1. Now, over here, for this x value of this mirrored point with him, we're going to go 1 unit to the left on this x-axis or this number line. And 1 unit to the left of -2 would be a -3. Notice the distance that each of these x values, -1 and -3, is the same distance away from the x value of the vertex. And one thing that we did mention to you in the first video, we mentioned for any pair of mirrored points, the y values will always be the same number. So whatever this number is going to be that we're going to find right there, that's associated with that -1, this will be the same identical value. These two squares will accommodate the same real number. So when we evaluate this, we don't have to evaluate both the -1 and the -3 inside that function. We just pick one of them, and I'll pick the -1. So now what we're going to do, we're going to find the y value when the domain is -1. We'll do it right here. That's going to be 3 times the quantity of -1 squared plus 12 times -1 plus 8. No, it's a little sloppy, but do your best to see it. Order of operations, take care of that power. It would be 3 times -1 squared, which is 1, plus 12 times -1 plus 8. Come down. 3, -12, positive 8. People, positive 3 coupled with positive 8 is 11. And 11 combined with -12, -1. That means this y value right down here is going to be -1. And over here, for its mirrored point, we don't have to evaluate any further. He's going to have to be -1 as well. Now you see, to me, that's pretty. That's nice. Now we only need one more pair of points, so let me just kind of erase some things right here. And let's go to the final mirrored point. To find him, it doesn't matter which one you begin off with, you don't have to go back to the vertex. Just begin at the furthest to the right x value that we've already accommodated, which is -1. Again, just think of this as a number line. To the right of -1, the first integer to the right of -1 on a number line would be 0. That's a nice number. Back over here, the very next integer to the left of -3, smaller than -3, -4. This y value and this y value will be the same. Let's use him. He's much easier to use. Oh, we can save some time. If x is going to be 0, 0 squared is 0, and 0 times 3 is nothing. That's going to be nothing. When the domain is 0, the range is going to be 8. So this is going to be 8 here, and this one's going to have to be 8 as well. And now we have our total of 5 ordered pairs. And now we'll plot them on the grid. People, you'll need to make sure that you have graph paper when you do it. You don't want to do it on regular line sheet. We need a graph paper. Now it really doesn't matter where you begin, because this parabola should open upward. I'll go ahead and start with the vertex -2, -4. Here's the origin. X is -2. And then we'll go down 4. 1, 2, 3, 4. Nothing is going to be perfect. I'm not working off of graph paper. There's the vertex. There's the lowest point on the graph. Now, doesn't matter where you want to go. Let's just do the next mirrored point, the first mirrored point. Let's do this -1, -1. That one right there. If x is -1, we're going to go down 1. And its mirrored image on the other side of the parabola. -3, -1. -1, -2, -3. It's going down 1. You see how they're facing one another? They're mirrored. There's that precious vertex. And now 0, 8. X is 0 all the way up to 8. And -4, 8. 1, 2, 3, 4 to the left. And up 8. Oh, let's say it's maybe right about there. And you can see that this parabola is going to be very narrow. It's not going to look like a bowl, but it is referred to as a bowl-shaped curve. It's just much narrower, and it will always be narrower as it's based on the size of A in the quadratic function. Now, I'm no artist, so mine is going to probably look crazy, and I'm just going to kind of come down, and you know, none of these points that I'm putting right now are accurate. And it's hard to work from this kind of a thing, but there's the turning point. And then onward up. Should put an arrow there and an arrow there, and there's the parabola. There's the graph of this quadratic function. If it was just perfectly done, every single point on this would satisfy that quadratic function. Now let's go to the 3 items. The first item that they want us to identify is the axis of symmetry. Here's what the axis of symmetry is. I told you it's going to revolve around the vertex. The axis of symmetry is always the equation x is equal to whatever the x value of the vertex is. You see, the axis of symmetry, I'm not going to make it in here, is this vertical line that intersects the vertex and cuts it in half. I'm not going to make that dotted line there. I don't want to mess that up. But how do we write the axis of symmetry? Well, if it's an imaginary vertical line, the equation of every vertical line is x is equal to whatever the x value of the vertex is going to be. Then in this case, x is equal to the x value of the vertex is -2. This is what you will write down as your axis of symmetry. It's the equation x is equal to -2. That's what the axis of symmetry is. Letter B, we want to define the domain and the range of this graph. The domain. Now recall back in, I believe it was chapter 2, when we were talking about identifying the domain and the range from a graph. To find the domain, you're going to take all of these points that are on this graph, and you're going to either move them up to the x-axis or move these down to the x-axis. And if you move all of the points from this graph down to the x-axis, we're going to find out that the entire x-axis is going to be filled up. Because remember, this side of the parabola, it's going to keep going outward. It's going to keep going out and out and out and out. And on the left-hand side, it's going to do the same thing. And so it's just going to keep going outward. And if you send all of those points that are up here, above the x-axis down, and these points up, they're going to fill up the entire number line. So let me give you a key truth about the domain of every quadratic function. The domain of every quadratic function will always be the set of real numbers. And we're going to use interval notation. It would be negative infinity, positive infinity. People, that is a guarantee. Every graph, every parabola will have as its domain the set of real numbers. Let's go to the range. The range, well, that's a different story. We're going to take all of these points and we're going to move them over to the y-axis. We're going to start with the vertex. If you move that over to the y-axis, there is the least value of your range. This is the smallest value of your range, which happens to be -4. All of these others, I'm not going to disrupt this y-axis, but all of these other points will move right over to the y-axis. The arrow will be darkened in. Your range begins at -4 and it goes infinitely in a positive direction, because as you move up the y-axis, you're getting larger. The smallest value would be -4. The largest value would be positive infinity. There would be the range of that graph. And then finally, we already pointed out that up here in letter C, they'll be either asking you to identify the minimum or maximum value and where it occurs. The minimum or maximum value occurs, or it's located where the vertex is. And here's the vertex, and it's at the lowest point of the graph. So for this graph, we have a minimum value. Now, there's two things that we need to define when we are identifying either the minimum value or the maximum value. We need to know where that minimum value occurs. Where does it occur? And then what is the actual value? So there's two parts to the overall answer when you're identifying either the minimum value or the maximum value, and it's all linked again to the vertex. The minimum or maximum value will always occur at x is equal to whatever the x value of the vertex is. Whatever the x value of the vertex is, that's where the minimum or maximum value is going to occur. So it's going to occur at x is equal to -2. That's where it's going to occur. You see, you have to move over to x is equal to -2 to be able to find that minimum value. It occurs at x is equal to -2. And what is that value? What is that minimum value? The minimum value will always be the y value of the vertex. So that minimum value is -4, and there is the overall finished product for the very first problem that we have done. Now hang in there, because I'm not just doing one. I want to do a second one, and I don't want to disrupt things, so let me just kind of get some things quickly erased And then we'll go to the second one and just show you one other one. Just get rid of that. Get rid of that for a moment and just kind of checking some things out. Let's go to number 2. And number 2, it looks like this. F of x is equal to a negative 1x squared, negative 2x plus 1. Notice its form. It's in the form that we're looking at. So let's identify first of all how the parabola is going to open. That's dependent on your a, the coefficient of x squared. Its coefficient is negative 1. So being that a is negative 1, that means it's going to open downward. So for this parabola, for this quadratic function, there's going to be a maximum value. Not a minimum, but a maximum, because it's opening downward. Now, the first thing that we need to do is get the x value of the vertex. So, a, I'll just kind of put it right here. The value of a is negative 1, and the value of b is negative 2. So now let's find the x value of the vertex right here. I'm going to bring down that opposite sign, and in place of b, negative 2, and that's going to be written over 2 times a, or 2 times negative 1. Well, the opposite of negative 2 is 2, or a negative times a negative is a positive. So we'll have 2 over negative 2, and that'll give us an x value of the vertex to be negative 1. Now let's find the y value of the vertex, and that means we're going to have to evaluate and find this. Find the value of f when the domain is the x value of the vertex. So f when the domain is negative 1 is equal to, be careful, bring down this opposite sign, make a house, put that value of x inside that house, it's going to get squared, negative 2 times negative 1, positive 1. Come down, bring down that negative sign, let's square that negative 1, negative 1 squared is 1, so this little outcome is going to turn out to be a negative 1. Let's get the rest of this. That would be a positive 2 and a positive 1. The 1s are opposite. They will cancel out. The y value of your vertex is 2. Now, let's speed it up here just a little bit. Here's your number line. The x value is negative 1. Move 1 unit. Go to 1 unit to the right of that negative 1 on that number line, and you're going to be at 0. Go 1 unit to the left on that number line, and you're going to be at negative 2. Let's use him. He's much easier to work with than that negative 2. Let's use the idea of 0. F when the domain is 0. I think we can do it right here. All of this, when 0 gets substituted, he's a 0. He's a 0. 1. So if he's 1, then this puppy right over here has got to be 1. That's nice. Let's get the final mirrored point. Come over here on the number line. You just finished up, you just located a 0. 1 unit, 1 integer to the right of 0, you'll be at a positive 1. 1 integer to the left of negative 2, you'll be at negative 3. So you can either evaluate when the domain is -3 or the domain is 1. Let's go ahead and use it when the domain is 1. Bring down that opposite sign, tuck that 1 and square it. -2 times 1 plus 1. Bring down that opposite sign. He'll turn into a -1. He'll be a -2. He will be a +1. They cancel one another out. The y value is -2. -2 is here. This then is going to have to be -2 as well. And now let's plot. Let's start with the vertex. -1, 2. X is -1 up 2. Right about there. There's the vertex. 0, 1. X is 0, y is 1. -2, 1. -2, 1. Over there, 1, -2. 1 down 2. -3, -2. -1, -2, -3. Down 2. Mirrored. Mirrored. Try to lasso this turning point around. It's not perfect, not by a long shot. Parabola, an inverted bowl. Axis of symmetry. X is equal to whatever the x value of the vertex is. The x value of the vertex is -1. The axis of symmetry is x is equal to -1. B, the domain. The domain is the entire set of real numbers. Because people is going to keep going out and out and out and out and out and out and out. Same over here. The entire x-axis is going to be filled up. The range, well, in this case, this is the highest point of the graph. Move that point over to the y-axis. It will be right there. The largest value of this graph is y is 2. That's the largest. And then it moves to the smallest, negatively, infinitely. So the largest value is 2. The smallest is -infinity. That would be the range. Finally, this parabola has a maximum point. So we want to identify the maximum value. And the maximum value occurs at x is equal to whatever the x value of the vertex is. It occurs at x is equal to -1, and its maximum value will be +2, the range value or the y value of the vertex, and there would be the final situation that we had to come up with and get. Now, when we move to the third video of 8.3, we're going to be looking at another style, a completely different looking quadratic function. And what will be nice about the quadratic function that we're going to be looking at in the next video, we will not have to calculate the vertex. We won't have to calculate the x value of the vertex nor the y. We will not have to do any work whatsoever to identify the vertex because it will be shown directly in the function. And so when we begin that next video, we're going to show you how this new form is going to evolve. I'm not just going to give you the form and ask you to accept something. We're going to give you a proof as to how this new form comes into existence. So we look forward to talking to you in some time, and we'll cover that. You take care of yourselves. Watch the video again and corral the understanding of the concepts that were talked about. Some of you are already probably aware of a lot of this, but some people are not. So we look forward to talking to you soon. Goodbye.